Hello everyone. This is Qi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Hello everyone. Welcome back to our Deep Learning course. Today we're starting Chapter 3, TensorFlow Implementation of Neural Networks 1. I'm your lecturer, Qi Jiaming. Let's dive into how to use TensorFlow to build neural networks, starting with the basics of data structures and image processing. First, let's clarify the learning objectives of this chapter. By the end of our study, you should master 4 key points. First, the concept of tensors and their operations. Second, techniques for image data processing. Third, how to implement a linear regression model with TensorFlow. Fourth, how to implement a logistic regression model with TensorFlow. Let's keep these goals in mind as we go through the content. Now, we enter part 3.1, the data structure of a neural network. The core data structure that neural networks rely on is the tensor. It's like the building block for storing and processing data in deep learning. Let's first understand what tensors are and how they're classified. Tensors are classified mainly by their dimension, and we can use Python's NumPy library to create their instances. Let's go through each type one by one. A scalar, a zero-dimensional tensor, like NP. Array 888, it has no axes, just a single value. Vector, a one-dimensional tensor, like NP. Array 1, 2, 3, 4, 5, it has one axis, like a list of values. Matrix, a two-dimensional tensor, like the 3-row, 4-column array here, it has two axes, rows and columns. 3D tensor, a three-dimensional tensor, like the example, with 3 groups of 2-row, 5-column arrays, it has 3 axes. Higher dimensional tensor, tensors with 3 or more dimensions, which are common in complex tasks, like video processing. Let's look at practical examples of tensors and their storage shapes. This is crucial for handling real data. The table on the slide summarizes 3 common types. Matrix, 2D, used for vector data, with a storage shape of samples. Features, samples are the number of data points. Features are the attributes of each sample. 3D tensor, used for time series data, shape is samples, time spans. Features, time spans, means the number of time steps for each sample. 4D tensor, used for image data, shape is samples, height, width, channels. Channels refers to color channels. 3 for color pictures, RGB, and 1 for grayscale images, which is also noted on the right side of the slide. Next, we move to part 3.2, image data operations. Images are one of the most common data types in deep learning, so let's learn how to read, process, and operate on image data step by step. Processing image data follows 5 key steps, and we'll use Python libraries like PIL and Matplotlib. Let's walk through them. First, read the image. Use from PIL import image and photo equals image. Open Photos or .jpg to load the image file. Second, change size, unify the image to 128, multiplied by 128 pixels with photo equals photo. Resize 128,128. This standardizes input size for the model. And third, matrix conversion, convert the image data into a 128,128. 3 tensor, since it's a color image with 3 channels. Fourth, scale change, divide each element of the pixel matrix by 255 to scale values to 0 to 1. This helps the model train more stably. Fifth, image display, use from Matplotlib import pyplot as PLT and PLT. Show to show the processed image, as shown in the example on the slide. We can also perform basic algebraic operations, addition, subtraction, multiplication, division, on image tensors to adjust their appearance. The slide gives 4 common examples. IM1 equals IM plus 0.5, brightens the image, adds 0.5 to each pixel value. im2 equals 1 minus im, inverts the image colors, subtracts pixel values from 1. im3 equals 0.5 multiplied by im, darkens the image, multiplies each pixel by 0.5. in4 equals int divided by 0.5, brightens the image, divides each pixel by 0.5. To show the results, we use PLT subplots 1, 4 to create a 1-row, 4-column figure and display each processed image in the axis. Note, the slide also mentions a prompt about clipping input data. This is because im2 requires pixel values to be in 0, 1 for floats, or 255 for integers, so values outside this range are automatically clipped to ensure correct display.